Hello, I'm Pinyu, and in my project, I used in vivo design to develop several novel antibiotic drug candidates to exploit an internal cell death mechanism that's contained in resistance plasmids. So when we think of public health emergencies, we often think of COVID-19, but there's actually another public health emergency that's currently emerging, and it's called antibiotic resistance. So I was first inspired to pursue this research into antibiotic development because of my grandmother, who sadly passed away from a bacterial infection in 2019. So as I researched into this issue, I found that one major mechanism of how this antibiotic resistance arises is through these vectors called plasmids. So plasmids contain toxin-antitoxin systems, which are also nicknamed as suicide modules because of their role as an internal cell death mechanism when the toxin fails to bind to the antitoxin. So because this interaction between the toxin and the antitoxin is mediated through protein-protein interactions, I wanted to find out in my research how we could specifically disrupt this interaction between the toxin and the antitoxin to artificially activate the system and cause cell death. So by identifying the residues that are responsible for contributing the majority of the binding energy, I hypothesized that the region from GLU66 to ARG72 on chain C of the KISS antitoxin will have the highest biological activity in comparison to control molecules and molecules that are targeting other regions of the toxin-antitoxin system. So using de novo design, I was able to construct my several novel antibiotic drug candidates that are targeted towards the hotspot residue clusters between the toxin and the antitoxin. And to predict the activity of my compounds, I used the Q-star model to classify my drug candidates as either active and inactive. And in my results, I found that 6 out of the 9 of them would be predicted as active. So I also wanted to evaluate the binding affinity between the the drug candidates and my protein target, and I found that both the Gibbs free energy and dissociation constant were statistically significant in comparison to my control molecules with a p-value of under 0.05. So finally, to evaluate for oral bioavailability and admit properties, I calculated the molecular properties and found that 6 out of my 9 drug candidates fell under suitable drug delivery guidelines. So in future research, I've currently been working with an expert in the field of toxin-antitoxin systems to explore some of the potential theoretical implications of using internal mechanisms in antibiotic development, since this strategy could have some very interesting implications in using antibiotics to help combat the antibiotic resistance crisis rather than contribute to it. But in the meantime, thank you so much for listening to my research, and I hope you learned something interesting about toxin-antitoxin systems.